This lab connects properties of electric current and magnetism through the use of an electromagnetic motor. It is important to note some concepts known before the experiment was performed. Electric current can produce magnetic fields, and charges moving in a magnetic field can experience a magnetic force. A voltage drop occurs across the electromagnetic motor, and a magnetic field is created by the attraction of magnets and a copper coil. We decided to alter the system of an electromagnetic motor in order to observe the change in speed of the rotation of the copper coil. Our problem statement was, what is the effect caused by change in electric current on the speed of an electromagnetic motor? Our main finding concluded that although ideal batteries were not used in this experiment, an increase in electric current and rotational speed of an electromagnetic current are directly proportional. Our independent variable is the number of 1.5 volt batteries, which theoretically alters the current. The batteries in this experiment are not ideal batteries, meaning the current will not increase in voltage as much as expected. The dependent variable being investigated is the rotations per second of the copper coil spinning in the setup, meaning the speed of the electromagnetic motor. In this setup, the coil becomes magnetized so that one end is the north pole and another is the south pole, causing the coil to spin since the magnets attract the opposite pole and repel the similar pole. The electric current produced by the batteries also creates a spin because force is exerted on the top portion of the wire so that the coil continues to spin. The wire is set up where half of one side is stripped and the other is fully stripped. This is required because it prevents the current from flowing for a half of each spin, according to Exploratorium 50, and inertia continues to carry the coil around each period without current. If it were not partially stripped, the polarized portion of the coil, opposite of the magnets, would stay at the bottom, closest to the magnets, so there would be no rotational force.
The rotations per second were calculated by videotaping the electromagnetic motor in slow motion and counting the number of times a point on the coiled wire passed by the magnets. Each video was split into 3 sections of 12 seconds, and the number of spins were then counted within each segment. To account for the 240 frames per second, which is 4 times the normal amount of frames in a video, the 12 seconds are divided by 4, which provides us with the real-time 3-second intervals. The average totals of the segments were then divided by 3 in order to determine the rotations per second. The potential errors and limitations are listed here.
So in our experiment, our model can be compared to a DC motor found in a typical children's toy. A DC motor has a rotor, which is labeled on the right-hand side inside the stator. The stator has the north and south terminals, while our model is positioned above a stack of magnets. Some DC motors, depending on what it's being used for, may have more or less amount of batteries and power than we had in our experiment, and the DC motor has wire windings between the rotor and armature, the electromagnet, while our model had one wire that was in a loop shape. However, both models did require magnets and a current going through. The scientific reasoning of our experiment was that the metals, needles, and wire created a loop circuit, which could carry current flow. The current flows from a negative battery terminal to a positive terminal, which creates a magnetic field. The coil acts as an armature. Magnets have both north and south poles. The north-south interactions attract, while the north-north and south-south interactions repel. Magnetic field isn't perpendicular to the magnet, so some parts of the wire's magnetic field will repel and cause the coil to spin. Since the insulation was removed from one side of the wires, this was done to periodically break the circuit, allowing it to pulsate on and off in time with the rotation of the coil. If this weren't to have been done, the magnetic field of the coil would align with the magnetic field of the magnet and stop moving due to attractions. The engine setup, so whenever the current moves, giving magnetic field, the coil can be repelled by the magnet's magnetic field. When the coil isn't actively repelled, the momentum carries it to complete the circuit, inducing a new magnetic field that can be repelled by the magnet. The coil spins until the battery dies, and then it spins in one direction because if it were to spin in the other direction, the magnetic fields would attract each other and not repel. The conclusion for our experiment was that an increase in electrical current results in an increase in the torque force to rotate the coil. Electric current and rotational speed of an electromagnetic current are directly proportional. More batteries equals more current. Because we had a parallel circuit with no resistors, when more batteries were added, particles in the circuit could move quicker, and so more batteries meant an increase in the voltage, meant an increase in the amps, which meant more current. Also, the equation F equals IL times B can be seen by the right-hand rule, as the magnets below the wire produce a magnetic field and force. The magnetic field and force causes the loop to spin by force pushing one direction on one side of the loop and the other direction on the other side of the loop. And below you can see that the increase in electric current increases the rotations per second.